we're ready to get started. So this is going to be our last lecture on entropy. So we spent lots of time talking about the second law of thermodynamics, and remember that very long statement of the second law of thermodynamics. Today we want to simplify it to see like what exactly does that second law of thermodynamics mean. And then we want to link entropy, which is an extensive state function as we derived using the Carnot cycle, into reversibility and irreversibility. And then we'll talk about the entropy change of the entire universe and see what exactly does the second law of thermodynamics tell us about the fate of the universe. And that's our very last part. We want to do a quick demo focusing on the same problem we solved before, which is the irreversible mixing of inert perfect gas, and see what exactly is entropy. What's the physical meaning of entropy? All right, so let's get started on our today's lecture. So before we want to get started, I want to remind you again, what do we know about entropy? So far, we know that entropy S is a extensive state function. And it's by definition, ds equals to dq reversible over T. Now, the question we're trying to solve in our first part is to try to get an idea about what does delta S, or how does the entropy change for our entire universe considering reversible and irreversible processes, and see how can we make general conclusions from these derivations. So first part, focusing on entropy change or delta S of a reversible system. All right, so what we're trying to do here is if we look at the entire universe, we have universe equals to system plus surrounding. All right, so remember our definition of the system and the surrounding. So system is the part of the universe we care about. Surrounding is the rest of the universe interacting with the system. Or because of the extensive nature of our entropy, we can write the change of entropy delta S of the entire universe equals to delta S of the system plus delta S of the surrounding. So when writing this equation down, effectively we're using the extensive nature of our entropy as a state function. All right, because remember our extensive function, you can write it as the sum of each part. So in here, let's consider a fully reversible process and thinking about what is the delta S universe of all reversible processes. So what does it mean when we say reversible? So in here, when we're saying reversible, what we're saying is all heat flow or Q are reversible. The other way to put it is a heat flow into the system will have the same magnitude as the heat flow out from the system. All right, so considering Q as describing the system, what we are saying is the Q into the system will have the same magnitude as Q out from the system. So what is heat transfer out from the system? Now the heat transfer into the system is Q system. The heat transfer out from the system is our Q surrounding. And because we have a reversible process, my Q surrounding equals to negative of my Q system. With me so far? So the whole point of having say, a reversible process, as we say the magnitude of the heat transfer in and out from the system will be the same. So the heat into the system, my Q system, equals to negative of the Q surrounding, or vice versa. They have the same magnitude, just different sign. So putting that in combination with our definition of entropy, we can get the following description, right? So this is what we said. S of the universe equals to S of the system plus S of the surrounding. So ds universe equals to ds system plus ds surrounding. And since the definition of entropy, S equals to dq reversible over T, we have the dq reversible over T, that's for the system. And on the right-hand side, we have the Q reversible of the surrounding equals to the negative of Q system. So the same magnitude will cancel out. So what we find out here is only using the definition of our entropy and knowing that my entropy is an extensive function, we can derive that the total entropy change of the universe equals to 0 for all reversible processes. So our conclusion here is delta S universe equals to 0 for all reversible processes. So for some of the questions you have, imagine you have all reversible processes, then using the Q system, you can derive the Q surrounding. But for irreversible processes, that's not necessarily true. So right now, this is the first section. We're talking about how does the total entropy of the universe change considering only reversible processes taking place. But we live in a real world, right? Obviously, our universe has lots of irreversible processes taking place. So what we want to do is, what about irreversible processes? Can we have a qualitative description in how does the entropy change for an irreversible process? So I built this figure here. It's coming from our Carnot cycle, but imagine instead of having two reversible isothermal plus two reversible adiabatic processes, now we have a irreversible adiabatic process. All right, so we can have this happening because it's irreversible adiabatic. My Q total equals to 0. It doesn't necessarily mean our Q reversible equals to 0. So we want to have the delta S between my point 1 to point 2, which is an irreversible adiabatic process. So how exactly do we want to build it? Let's imagine we have these dots, right? So that's the 1, 2, 3, 4. We have 4 total points. When we're writing that delta S out, what do we know? We know that our delta S of a cyclic process, whether it's reversible or not, must be 0 because my entropy is a state function, right? So if we build a hypothetical, cycle, so that it's 1 to 2, 2 to 3, 3 to 4, 4 to 1, right? So in that hypothetical cycle, my delta S of the cycle must equal to 0. That's only using the nature of entropy being a state function. Now in this cycle, what do we have? We have the delta S between 1 to 2, or we have the S2 minus S1, or delta S 1 to 2, plus S1, S3 minus S2. So this is the delta S 2 to 3, plus S4 minus S3, or delta S 3 to 4, plus we're finally at S4 minus S1. S1 minus S4, sorry. Right, so 1 to 2, 2 to 3, 3 to 4, 4 to 1. So you can write it as this. All right. We take this from our kernel cycle. So in order to simplify our discussion, let's just say we manually set my step 2 and 2 to 3 and 4 to 3. So these two steps being my reversible adiabatic steps. So that gives us my delta S 2 to 3 will equal to 0. And my delta S 4 to 1 will equal to 0. With me so far? And on the top, we have our reversible isothermal process. So what do we have? We have my delta S 3 to 4 equals to Q 3 to 4 over TH. Because it's isothermal, so our temperature is constant. We can take that temperature out from the integral, and hence we have this expression, Q 3 to 4 over TH. All right, so what we're doing here is building a cyclic process containing one irreversible step, which is your step from 1 to 2. And for this entire cyclic process, we know the total delta S will vanish to be 0. So in here, a few things we know. Now, for these two green ones, the 2 to 3 and 4 to 1, these are my reversible adiabatic. So since they are reversible adiabatic, my Q reversible equals to 0, my delta S equals to 0, so these terms go to 0. With me so far? And the next one, we have our 3 to 4. So this is our reversible isothermal process, or we have Q 3 to 4 over TH. And what do we have left? We have what we want, right? So the change of entropy for this irreversible step between 1 to 2 plus the Q3 to 4 over TH equals to 0. So in this whole process, what we're using what we know, right, with the definition of entropy, and then using the nature of entropy as a state function, we build a hypothetical cycle containing 3 reversible steps and 1 irreversible step. And hence, we have a connection between my delta S 1 to 2 to this term, the Q3 to 4 over TH. All right, so I'm going to move to our next page. So what do we have? So in our diagram, we derive that my delta S 1 to 2 equals to the negative of Q 3 to 4 over some temperature H. All right. Next up, we want to use our first law of thermodynamics to link this expression here to our jargon-like long description of the second law of thermodynamics. So in here, what do we have? We have delta U equals to Q plus W for this closed system at rest, no external fields. Or the other way to put it is if we take the cyclic integral of du, that must equals to the cyclic integral of dq plus dw All right, so that's taking the cyclic integral of the overall work and overall heat of the cycle. Now in here, what do we have? We know that this dq part, we have 3 adiabatic processes. So now in our first law of thermodynamics, we don't have our Q reversible anymore. We're talking about any adiabatic processes will have Q equals to 0, reversible or not. So in here, my dq just equals to my Q 3 to 4. And we say other 3 are adiabatic. And for our work part, this just integrates to be my line integral, the total work. Or the other way to put it is we're focusing on this Q 3 to 4 term and use our first law of thermodynamics to try to get an expression of what is the sign of my Q 3 to 4. So in here, what do we have? We have the total heat equals to Q 3 to 4, total work equals to W, and my cyclic integral of the internal energy must be 0. Or what do we have? It's Q 3 to 4 plus work equals to 0. Or you can write work as negative Q 3 to 4. All right. So how come this gives us a knowledge about what is the sign for my heat? Now thinking about what does the sign of Q mean? A positive Q means the system is absorbing heat from the surrounding. A negative heat means the system is giving out heat to the surrounding. And for work, the same idea. A positive work, meaning we have surrounding doing work on the system, and a negative work, meaning the system is doing work on the surrounding. So this is a little bit of the logic gap. Let's assume my heat 3 to 4 is positive, saying the system is absorbing heat in that isothermal process. Now, in that process, my work must be a negative number. We did this derivation using our first law of thermodynamics. This is this part's derivation. Right, assuming my heat transfer between 3 to 4 is positive, my work is negative. So what is the physical meaning of that process? So that means for this irreversible cycle, the only effect is that the cycle intakes heat, which is a positive heat, Q3 to 4. And the only work, that's the only outside output from the cycle is some kind of work. Or the other way to put it, the sole effect of this cycle is to extract heat, which is the Q3 to 4, from a hot reservoir and completely convert it into ordered mechanical work to the surrounding. All right, so this is why we say this statement violates the second law of thermodynamics. So go back to our old jargon-like saying, the second law of thermodynamics forbids that the sole effect of any heat engine being transferred disordered heat into ordered mechanical work. Now, this is a false statement. All right. So using the first law and the second law of thermodynamics, we get to our final conclusion that this term, the Q 3 to 4, must be negative. And remember, this one we're talking about the whole delta S for our adiabatic irreversible process equals to the negative of Q 3 to 4 over some temperature. What do we have? We have Q3 to 4 being negative. We have a negative in front of it. So my delta S for this irreversible adiabatic process must be a positive number. All right, so you see this in our midterm exam. So sometimes in this class, it's more important to get a qualitative understanding. And if this term is 0, positive, or negative, than getting a numeric answer. This is a good example in why do we care about it. We did our derivation without doing any actual plug-in number, but our whole take-home message is this term, the heat must be negative, otherwise we're violating the second law of thermodynamics. Yes?
Why is the step between 1 and 2, why is it negative?
So that goes back to our original setting. Remember, we're building a hypothetical cyclic process, right? So in this cyclic process of 1, 2, 3, 4, 1, what we have is this cyclic process, delta S must equal to 0, because S is a state function. And then we write out what does each step mean. So delta S between 1 to 2 is S2 minus S1. That's our delta S1 to 2, and the same applies. All right, and in this whole process, we see that, all right, so here is our Q3 to 4 over TH plus delta S1 to 2 equals to 0. And hence, my delta S1 to 2 equals to negative of Q3 to 4 over TH. All right, what we're using here is the nature of delta S as a state function. So we're building hypothetical path for that irreversible process. Or the other way to put it, what we find out is delta S 1 to 2 must be positive for this irreversible adiabatic process. So this AD, sometimes we abbreviate it for adiabatic process. Or the other way to put it, since the system we're talking about is our entire cycle, it's my irreversible process between 1 to 2. So now imagine we have any system that undergo an irreversible adiabatic process. That delta S must be larger than 0. All right, so the whole point of our derivation here is thinking about the irreversible process and how does delta S change for that irreversible process. And in this case, we build a special system that undergoes adiabatic irreversible process. And our derivation tells us the delta S of the system that undergoes an adiabatic irreversible process in a closed system must be larger than 0. Now, how can we generalize this conclusion? Right now, we're thinking about a closed adiabatic system undergo irreversible processes. Now, in order to generalize our conclusion, what is an isolated system? So recall what we covered. An isolated system is adiabatic and closed by definition, right? An isolated system does not interact with the surrounding. It doesn't transfer heat with the surrounding. It doesn't transfer matter from the surrounding. So that doesn't transfer heat is adiabatic and closed, no matter transfer. Or we can generalize what we said before from this delta S system, irreversible, adiabatic, closed, into saying an isolated system into saying that an isolated system must have delta S larger than 0 for irreversible processes. Yes.
So, you say that entropy is a state function, right?
Yes.
And like just before this, we said that for reversible processes, the entropy is for reversible adiabatic processes, the entropy change is 0. But now we're saying that for an irreversible adiabatic process, the entropy change is positive and close to 0.
Mm-hmm.
So assuming that you have the same beginning and end states, but the process is reversible versus irreversible, how can they?
So here's the thing. The difference comes from what we're trying to do here. Now your reversible, fully reversible, and irreversible processes cannot have the same initial and final state because their delta S will be, okay, so the way to put it. In this example, what we have several reversible steps, all right? But what we're doing here is we have your initial and final state being 1 to 2. So what we're doing here is if you want to build a reversible path to calculate my irreversible process between 1 to 2, what we're building is this entire thing, 2 to 3, 3 to 4, 4 to 1. So they're not necessarily the same path. Does that make sense? So we can only calculate delta S along a reversible path. Does that answer your question?
Wouldn't that make entropy not a state function then?
It is a state function because in this case, the whole point, the whole reason we can do this derivation is because entropy is a state function. So what was your question again? Let's just restate it.
I mean, you've built this reversible path. So we say that this is an adiabatic irreversible process.
Mm-hmm.
And we've concluded that the delta S is positive for the system.
Mm-hmm.
If we make this now a reversible adiabatic process,
We cannot make a system both reversible adiabatic and irreversible
no,
adiabatic.
that's what I mean. Like if we just say, oh, this is now a reversible process that's adiabatic with the same start and end points.
Oh no, so here's the thing. You cannot build, so in this case, it's actually, the logic goes backwards. So this is an irreversible adiabatic process. We did our derivation to say that delta S must be positive. That means we cannot build a fully reversible adiabatic path linking your initial and final states. With me so far? So that's where the logic gap is. In this part, we're demonstrating that for irreversible adiabatic processes, we have delta S larger than 0. And for reversible adiabatic processes, delta S equals to 0. Right? So they cannot have the same initial and final points. You can try it, and if you build that reversible adiabatic path, I mean, the same as the adiabatic irreversible path, you're proving the second law of thermodynamics is wrong. We have people challenging that before, but try it. Nevertheless, so with that in hand, I like that question though, so do give it careful thought and see why it's not possible. So back to here, to our isolated system. So far what we did is we start by a process that's irreversible, adiabatic. And then we generalize that conclusion to say a irreversible adiabatic closed system is effectively to say it's an isolated system undergo irreversible processes. And the one last step to go is to say that during irreversible processes, the system and surrounding are only interacting with each other. So it's irreversible. My total delta S of the system and my delta S of the surrounding must be larger than 0. Right, so if the process is irreversible, heat flow irreversibly from your system to surrounding or vice versa, nevertheless, both cases, they're irreversible processes. And my system plus surrounding equals to the delta S of the universe. That gives us the delta S of the universe is larger than 0 for irreversible processes. All right, so in this part, we did a seemingly long derivation, but the whole point is we start by looking at the entropy for reversible process, and we find out that delta S universe equals to 0 for all reversible processes. And then we start from a very special case, which is irreversible adiabatic process. By building hypothetical cycle and using the first law and second law of thermodynamics, we prove that that irreversible adiabatic process must have delta S larger than 0. And taking that together, we got our second law of thermodynamics rewind. So that's saying the change of the total entropy of the entire universe will always be larger than or equal to 0. And in here, since we're saying, we're stating this new state function, again, we defined this new state function S, which is a extensive state function, has the property of delta S universe larger than or equal to 0 for all processes. Yes?
Conceptually, does this kind of go hand in hand with, for things to happen spontaneously, it has to have a positive?
We're getting there when we're talking about entropy and equilibrium. But whether it's spontaneous or not, that's linked to Gibbs free energy, and we'll talk Gibbs free energy in our later lecture, actually next Wednesday. Now, with this in hand, we want to pause and think about one thing that's a little bit less intuitive. Thinking about equilibrium. Well, we're saying thermodynamic equilibrium. What we have is that the entropy is maximized when the system reaches equilibrium. So this is very counterintuitive. So think about it this way. When we plot entropy with time, we just demonstrated that the entropy can only increase for any processes, whether it's reversible or not. All right. So in the process before equilibrium, we have our ds larger than 0. So we have irreversible processes going on before equilibrium. And at equilibrium, we have the change of entropy goes to 0, because at equilibrium, remember, we only have reversible process happening. The composition is at fixed. So in this case, I just want to clear this point a little bit, that when we say thermodynamic equilibrium in an isolated system, that's saying the system's entropy is maximized. So we only have reversible processes taking place at equilibrium. All right, so this is our first part, linking entropy to reversibility and equilibrium. We'll come back to this figure later on. Do you have any questions before we move on to talk about the physical meaning of entropy? Yeah.
So just when you go up a little bit, when it says that the delta S of the universe is going to be always greater than 0, is that still
Greater or equal to 0.
Greater or equal? Is that still for just irreversible processes?
Well, it's greater than 0 for irreversible process. It equals to 0 for reversible process.
Oh, that's right. Okay.
But for any processes, it's always greater or equal to 0. Next up, let's look at the physical meaning of entropy. We've been talking about entropy for a long time, right? For right now, what we know is we know entropy is a state function. But what exactly is entropy? That's something of a myth right now. So let's go over it step by step and try to give entropy a meaning. Right? So what we did, so again, as a review, in our previous lectures, we linked thermodynamic laws with state functions. Right? So in our zeroth law, we define our state function, temperature. And in our first law, remember we say there exists an extensive state function, which is total energy. We have delta E equals to Q plus W for a closed system. And we have our delta U equals to delta E for system at rest, no external field. And we have conservation of our energy. Right, so our first law is our link our energy to our first law of thermodynamics. And then in our second law, again, we define our thermodynamic state function, which is entropy. And back to our picture of saying entropy S is maximized at equilibrium. Again, we went over this logic flow and thinking about, okay, now we accept the fact entropy is maximized at equilibrium. Now, trying to give entropy a physical meaning, we want to give it a careful thought. What else is also maximized at equilibrium? And that thing that is maximized at equilibrium must somehow be related to entropy. So this is a little bit vague, so let's give you a special case. Thinking about our mixture of two ideal gases at constant temperature and P. What do we know? We know that these gas molecules do not interact with each other. We know that the motion of the gas molecules are completely random. And thinking about why the mixing of gases is irreversible. Right, so if you have like two gas molecules, on the left-hand side, they're separated by solid wall. Now we remove that partition, and then the system will eventually proceed to equilibrium where my gas molecules are evenly mixed with each other. So what's the difference between these two states? Now, if you think about what do we have? On the left-hand side, this is a low probability state. And on the right-hand side, we have a high probability state. Right, so on the left-hand side, we can actually calculate this low probability state. The gas molecules' movement are independent from each other, so each molecule D will have like 50% chance to stay left, 50% chance to stay right. Now, given enough molecule and let it rest, it will eventually reach that equilibrium state. Or I did a little simulation. I'm just going to jump ahead. I write a little code to run the simulation. What do we have? This is our initial state. Left are 500 red dots. Right is 500 blue dots. Now I ask the script to do one single thing. It gives each dot a random direction and random force and asks the dot to start moving. It does not bounce on the wall. It does not interact with each other. And give it enough time, what we have is a final state where my gas molecules, red and blue, are mixed with each other. So if you look at the curve of counting the number of red dots on the left and the number of blue dots on the right, what do we have? We have this number start from 500, and then it just instantaneously drops until it fluctuates around equilibrium. That's only 500 gas molecules. Imagine you have one more of molecules on the left, one more of molecules on the right. So that fluctuation will become more stable. All right, so this is a more straightforward picture to tell you, hey, what else is maximized at equilibrium? It's a probability of that state happening. Or the other way to put it is the equilibrium thermodynamic state of an isolated system is the most probable state, has the highest probability. Yes?
So entropy is increasing as you get closer to that state?
Well, yes, entropy will increase. Entropy will increase until we reach that equilibrium state, and then entropy will become a constant. All right, so far, in this demo, what I'm trying to show is, somehow my equilibrium state is related to the probability of that state happening. With that in hand, let's do a more quantitative analysis. So go back to our mixing of gas molecules. So now imagine entropy is some kind of function of probability. So we'll do this stepwise, trying to build a link between entropy and probability. So in here, assume that entropy is a function of probability, just a random function. I'm just going to say S equals to some function of probability. So know that this P is probability, not pressure. So using probability theory, what we have, considering a system composed of two independent, non-interacting parts, right? So like what we had two chambers separated by a rigid, impermeable adiabatic wall. So the total probability of event 1 and event 2 happening is the sum of my event 1 and event 2. So this one. Wait, actually, back to square one. Let's talk about entropy first. So considering the system composed of that two parts not interacting, so the total entropy of 1 plus 2, giving my entropy as an extensive function, equals to S1 plus S2. All right, so writing it back into our function, we have some function, H, as a function of P1 plus 2. So this P1 plus 2 is the probability of state 1 plus 2 happening at the same time, equals to F P1 plus F P2. Let's just plug in this number here. And then we're ready to use our probability theory. So the probability that two independent events both happen is the product of the probability of each event. So it's like you toss one coin, you toss another one, and the probability of having two heads is 1/4. So the other way to put it is our P, 1 plus 2, equals to P1 times P2. All right. Or translating this equation here along with our probability theory, we get an expression that some function, the same function, P1, P2, must equals to that function of P1 plus that function of P2. Or the other way to put it, we want a function that satisfies hxy equals to fx plus gy. And in this case, the logarithm function is the only solution to satisfy this condition here. I'll skip the mass derivation in y logarithm. It's the only solution. But what we end up having is entropy equals to some constant times logarithm of probability plus a constant a. All right, so in this part, what we're doing is start from the very beginning. Just knowing that, well, entropy and probability of that state must be linked by some function. And we use the nature of entropy as a state function to write S1 plus 2 equals to S1 plus S2. We give it a random function, and then using probability theory, we find out that logarithm function is the only solution to this, to satisfy this condition. So with this in hand, let's go back to our mixing of ideal gases and redo our derivation on the entropy change for mixing of ideal gases and compare our result with our previous derivation. So back to our mixing of ideal gases. Again, considering the process between state 1 to state 2 after remove the partition, we have an irreversible mixing of two perfect gas at constant temperature and pressure. Now we have write S as a function of, as a logarithm function of probability, or the other way to put it, we have S equals to K ln P plus A, right? K and A are constant. So my delta S of S final minus S initial equals to K times the logarithm of P2 over P1. So in here, P is probability, not pressure. So how do we calculate the probability of my final state and the probability of my initial state? So this is our initial state. What do we have here? So the probability of my molecule D on the left-hand side equals to 1/2 to the exponential of number of molecule D times 1/2 to the exponential of number of molecule E. Right, so this 1/2 comes from we're dividing my chamber in 1/2, 1/2. You can make your life harder by dividing it to 1/3, 2/3, and then do the same kind of calculation. All right, so this one is just probability. This big N represents the number of molecule. You can calculate the number of molecule using the Avogadro number. And assuming my ND equals to NE, this is not necessarily true, but let's assume your ND equals to NE, you'll get the result as P1 equals to 1/2 to ND. And for my equilibrium state, that's my most probable state, right? Or the other way to put it is my equilibrium state is infinitesimally close to 1. So taking that together, what we have is my S2 minus S1 equals to K ln P2 over P1. My P2 equals to 1, my P1 equals to 1/2 to ND. And what we have here is K ln 1 over P1, or K ln 2 to the 2ND. And for exponential in the logarithm, we can take it out to be 2ND K ln 2. Right, so this is our delta S for mixing of two perfect gases in two chambers, assuming they have the same number of moles. So back to what we had derived before. We have delta S calculated from the dq reversible over T equals to negative number of moles times R ln mole fraction minus an E R ln mole fraction of E. So in here, my ND equals to an E, my mole fraction equals to 1/2. So we plug that in, we got 2 ND R ln 2. All right, so this is the example we did in our last lecture when we're talking about calculating the change of entropy for mixing of two inert ideal gases. And compare these two results. What do we have? My ln 2 is the same. We both have 2 in front. What we end up having is 2 ND K ln 2. So this is a derivation coming from our probability derivation must equals to 2 number of mole of D times R ln 2. So in here, my ND is a number of D molecules. And on the right, my ND is number of mole of D. And what we have is a relationship between this constant K and our gas constant. What we have is K equals to ideal gas constant divided by the Avogadro number. And that's 1.38 times 10 to the negative 23 joule per Kelvin. And this is our Boltzmann constant. I'm a little bit above time, but as a take-home practice, you might want to redo our midterm exam question 2-5, in which we calculated delta S of mixing of two ideal gases using this equation here. Redo that question with our probability equation and check your answer to see if they fit. They should, all right? And later on, I can also share you the note in how I do the simulation, so you can play around with that simulation, change the number of molecules, and see how does it change our resulting picture. All right, I'll be around answering questions. I'll also be around in my office hour tomorrow if you have any other questions.